In today's lesson, we are going to be looking at problem solving with combinations. So we're going to be looking at different scenarios, and we're going to be looking at just some ways that we can kind of speed through the process in some of these problems. So it's not going to apply to every combination problem we come across, but again, when we kind of look for keywords or we're looking at scenarios, we might be able to use these steps or these strategies rather than kind of going the long way. So first thing we're going to look at is distinct items, where we're looking at each item is different. So how many selections are possible from a bag containing one red, one blue, one green, one yellow, and one orange marble? And we must choose at least one. So a couple things here. How many selections are possible? So again, just basically how many different ways can we pull something out in terms of having them in our hands, not in terms of how we pull them out, right? But just in general, the marbles that we might get. So that indicates it's a combination. And then the second thing is must choose at least one. So by choosing at least one means we have more than one way, or there's multiple cases. So again, it comes down to reading the scenario and understanding what it's asking. So we have to choose at least one. So at least one could mean we have one item. So if we have one item, let me just change some of the sizes here. So multiple cases. And if we're looking at least one item, that means we could have one item, which means we have 5 marbles choosing one, or, and by or we mean add, we could have 5 marbles, choose 2 of them, so we have 2 items or 2 marbles that we pick, or, which means again we're adding, we have 5 marbles choosing 3, or 5 marbles choosing 4, or 5 marbles choosing 5, right? So we could either pull 1, 2, 3, 4, or 5 marbles. Now, if we go through and we calculate all of these, add them all up because they're multiple cases, it's one or the other, and so on, we would end up with 31 ways or 31 different groups of marbles that we could pick from if we had to choose at least one. Now, with 5 marbles, 5 items, 5 different items, that's not too bad. But what if we had more than 5? 10 items, 20 items, 30 items, right? We wouldn't want to have to go through this tedious case of adding up 1 item plus 2 items plus 3 items and so on and so on. Now, there is a faster way. So in general, if we're looking at something where we're looking at all different items, and we want to look for the total number of combinations containing, and this is key, at least one item chosen from a group of n distinct objects, so basically just different items, we can use instead 2 to the power of n divided or minus 1. Now, what does this really mean? Well, the 2 represents the number of options. The number of options per item. And what we mean by number of options per item is either we could select it or not select it. So each item has 2 options. Either we select it or we pull it or we don't pull it. The n represents the number of distinct items. Right? So number of distinct items, or in other words, we could say the number of different items. Right? So if we go back to that marble question, each marble was different. So they were distinct. And the one here, when we subtract 1, this represents the null set. And what we mean by the null set is that no items are chosen. So because we're saying at least one, we subtract the one scenario where all of them could not be selected, because we want to choose at least one. So if we had to think about how many different ways could we pull a marble or pull an object, or how many different groups could we create, if we didn't have the restriction of at least one, we would just do 2 to the power of n. If we did have the restriction of at least one, then we subtract the one, or we subtract the one scenario where we don't select any of them. So if we were to go back up to this last scenario and use that kind of shortcut, so it'd be 2 to the power of 5, because there's 5 different objects, minus 1, which would equal 31. So again, that's a kind of a shortcut when we're looking for at least one. Now, in these cases, or in that case, we had all distinct items. If we have some indistinguishable or identical objects and we still have to choose some or at least one, so again, we're still going through that scenario, but in this case, we have identical objects. So maybe we had 2 red marbles, 3 blue marbles, 1 green marble. And we wanted to figure out how many different combinations could we take, or could we have, if we had to select at least one. We have A plus 1, B plus 1, C plus 1, all multiplied, and then minus 1 combinations. So again, the minus 1, this is our null set, or that one scenario where there are no items being chosen. The A, B, and C represent the number of objects. So number of items, or number of item A, we could say. So the first item, B, is looking at the number of item B. Right, so how many of the second indistinguishable object do we have? And then same with C. So let's go through and look at an example of how this would work. So again, we go back to the marbles. A bag of marbles contain 1 red, 3 blue, and 2 green marbles. If you pick up some without looking, how many different selections might you make? So we're going to use that formula because we're looking for some, or basically we're assuming that we have to select at least one marble. So A plus 1 times B plus 1 times C plus 1, and then we're going to subtract that null set, or that one scenario where all the options are, or we don't select anything. Right? So what A, B, and C, what do those represent? Well, A would represent, we could say, the red, B would represent the blue, and C would represent the green, the number of green marbles. Because again, I could pull 1 blue, or I could put 3 different choices for pulling blue, plus the 1 choice for not selecting any. So when we go to our scenarios then, we have A plus 1, or 1 plus 1, because I could pull the 1 red marble, or I could not pull it. And I'm going to multiply that by B plus 1, or the 3 blue marbles that I could pull, plus the 1 scenario where I don't pull any, multiplied by C, which is 2, the 2 green marbles, plus the 1 scenario where I don't pull any, and then I'm subtracting 1, again because the 1 scenario where they all are, or none of the marbles are selected, so I don't want to have that option. In the end then, we have 2 times 4 times 3 minus 1, and we get 23 ways. So there are 23 ways in total where we could select some marbles, or at least one marble. Now you could go through and look at every scenario, right? Picking 1 marble, picking 2 marbles, picking 3 marbles, right? And you could look at the different colors. You could look at that scenario to help us. or because order doesn't really matter, you could say we have 5 marbles choosing 1, and so on and so on. Or sorry, 6 marbles, right? So different ways you could go through it. You could look at every scenario possible, or you could kind of use this kind of shortcut. Example 3. A director of a short film has 5 rock, 2 blues, and 3 jazz pieces he can select from. How many ways can the director choose 3 pieces if he wants to include jazz? Right, so again, choosing 3 pieces indicates that we're looking at combinations. Right? It doesn't matter what order he chooses them in. He just wants to make sure that from his selection, he has at least jazz, and he's just making a selection of 3. It doesn't matter what order they come in. So in this case, there's 2 different ways you could do it. You could choose to do the direct way, which would be looking at every scenario possible, or you could looking at the indirect way. And we're not going to use what we just kind of learned, the 2 to the power of n or the multiplying, because we're not looking for how many ways can we choose just 3 pieces or at least 1 piece, right? We're looking at a little bit more specific. So here we have multiple cases if we're going in the direct route. So case 1 would be 1 jazz piece. So how many ways can I choose at least choose 1 jazz piece out of the 3? Well, I have 3 jazz pieces in total. I'm going to choose one of them, multiplied by the 7 remaining pieces, choosing 2 of them. So this is for the jazz, and this is for the no jazz. Case number 2 would be, what if I chose 2 jazz pieces, or 3 of those 3 of the pieces that I need to choose, say 2 of them were jazz. So again, now I have 3 jazz pieces, but now I'm choosing 2 of them, and then I have 7 still non-jazz, and I'm going to choose 1 of them this time. So looking at the 2 parts. And finally, case 3, what if all 3 of those pieces that I chose were jazz, or the director chose? So I have 3 jazz pieces, choosing 3, multiplied by 7 other pieces, choosing 0, which would just work out to 1. Right, there's only one way that I can choose all 3. And because it is one case or the other, I would add all of them up and I would get 85 ways. So there are 85 ways that I could choose 3 pieces of music, and I have to include jazz, or the director has to include jazz. Let's look at the indirect way. Indirect, remember, is the total number of ways without any restriction. So how many ways can we choose 3 items? Minus the opposite or the complement of what we're looking at. And the complement of this case is no jazz. Right? So if I want to include jazz, that's the same thing as saying at least 1 piece of jazz. So the complement is no jazz at all. For the total number of ways, we want to make sure that when we're not dealing with probability, the total number of ways is just the number of ways without any restrictions. So again, in general, we're just choosing 3 pieces from 10 pieces of music in total. So 10 choose 3 minus, and then no jazz would be, I have 7 options choosing 3 of them, multiplied by the 3 options of jazz choosing 0 of them. Do I need to include that second part? No, not really, because it doesn't really affect my answer, right? Because there's only one way to choose 0 of them, and when I multiply by 1, it doesn't affect anything. However, I do like to have it in there because if we look at the direct case, we did need to have that second piece. So it's more kind of out of habit, if anything, and it allows us to kind of keep good habits. And again, if we go through and we solve, we would find that we have 85 ways. So again, either way we go through and solve this, we end up with the same answer. Example 4. Lindsay, Megan, and their 4 friends want to join the cheer squad. if the group only has 3 members, or if they're only allowed to make a cheer squad or a group in cheer squad of 3 members, how many ways can the 3-member squad be formed? Well, Lindsay and Megan and their 4 friends, we have 6 total people, and I'm going to choose 3 of them. So that means there are 20 ways. So there's 20 ways I can make a 3-person group out of these 6 friends. Now, how many of these ways contain Lindsay? Well, if we look, or if we break it down, what the group has to contain. So we have the one piece of Lindsay, and we have the other piece of members that are not Lindsay. Oops, if I can spell the name right. So if we look at choosing Lindsay, there's one Lindsay, we're choosing her, multiplied by, because it's Lindsay and other members, multiplied then by 5 other members, choosing 2 of them, which in this case would give us 10 ways. How many ways do not contain Megan? Now this is similar to what we just kind of did, even though it's a different name. Let's look at the 2 components of our group. We have Megan and we have not Megan. So there's one Megan, but we're not choosing her. So 1 choose 0, multiplied by, there's 5 remaining members, and we're choosing 3 of them. We get 10 ways. So there's 10 ways to choose or to not contain that person. And you might say, well, how is that the same? How do I get the same answer? Remember, if we go back to the factorial notation for combinations, the first answer it had to include one person, would have been 5 factorial over 3 factorial times 2 factorial. And in this answer, so this was B, C would have been 5 factorial over the 3 factorial, other way around, 2 factorial and 3 factorial. So it's kind of that scenario that we talked about where they had the same answers, because you could argue it's the same as choosing 2 people from 5 or choosing 3 people from 5. You still get the same answer in the end. And how many contain both Megan and Lindsay? Well, again, if we look at the 2 components, we have Megan and Lindsay in the group, and then we have not Megan and Lindsay. So out of Megan and Lindsay, we have 2 people, choosing 2 of them, we're choosing both, and then we have 4 remaining friends choosing 4, which gives us 4 ways, right? Because if order doesn't matter, 2 of those spots are already taken up, so there's 4 different ways that we could choose that 4th person because there are 4 friends. The biggest thing from that one is just making sure you break down the group into the 2 components to see where you're selecting from. Right. Number 5. So the fun part, we might have to include permutations and combinations. So example 5, how many 5-letter codes can be formed from 2 different vowels and 3 different consonants? So here we have 2 parts. So this 5-letter code, we've talked a lot about codes previously, and codes indicate an order. So in this case, order matters. Right? When you're putting things into a code, order matters, so we're looking at permutations. But in terms of selecting what things we could use, it doesn't matter what vowels I choose of the 2 different vowels or what consonants I choose. Right? It doesn't matter what order I pick those 2 vowels. What matters is that I've selected them, I've chosen them. So in this case, for this part, order does not matter, which means we're doing combinations. So in this case, we have to do 2 parts. First, we're going to do our combinations. So how many ways can we choose 2 different vowels? and 3 different consonants, and then we're going to look at the order. So let me kind of keep it color-coded. So vowels, then consonants, and then the order. So for the vowels, assuming A, E, I, O, U, right? So 5 vowels, choosing 2 of them, because we can have 2 different vowels, multiplied by, and 21 consonants, choosing 3 of them. So that's how many different combinations of vowels and consonants I could come up with. And I'm going to multiply that by 5 factorial, which is how I can create a 5-letter code, right? Because 5 options of those for the first one, then 5 for the second, or then 4 for the second, 3, 2, and 1, and so on. And in the end, we end up with 1,596,000 different codes. Now, how many of these combinations contain or include the letter C? So in this case, let's look at what our combinations or our group of letters is going to consist of. Right, our order is going to remain the same. We're still going to have the 5 factorial because we're going to be taking those 5 letters and arranging them into 5 different spots. But what is our group going to consist of? Well, again, the vowel is not going to change. We still have 5 vowels. We're choosing 2 of them. We're going to multiply that if we need to include C. There is one C, and we're going to choose that one. And then we have our remaining consonants. So I have 20 remaining consonants. I'm choosing 2 of them. So that is what our group of 5 letters consists of. 5 vowels, choosing 2 of them. The one C, choosing it to include it. And then the 20 remaining consonants, choosing 2 of them. Right, I'm only allowed 3 in total. I've chosen 1 for the C. The other 2 are going to be from that 20. And then we multiply by the 5 factorial because of the 5 different spots that we could place our letters, or the 5 different positions for arrangement. In this case, we get 228,000 codes. So this lesson just kind of gave us some different scenarios that we may come across when dealing with combinations, and especially problem solving. Could be scenarios where we have to select at least one or some of the items, right? So rather than go through every case, we had some new formulas to kind of help us speed through that process. Looking at certain scenarios where we might have to use indirect or direct method. Looking at different components of groups. We saw that in the cheer squad question. And then looking at scenarios where we had to basically come up with different groups, as well as then arrange the items in the group. Right? So a bit of a joining of the permutations and combinations. Right? So make sure you are going through and doing some of the homework questions, because it does give you some more scenarios that you can look at and just get you used to problem solving in these different types of questions. But again, it's just using combinations, sometimes permutations, but just breaking down what are we selecting for our groups.